Hey everyone, welcome back. In this video, I'm going to walk you through a MATLAB script that simulates a complete solar power system, a PV array, a boost converter, and a digital MPPT controller using the Perturb and Observe algorithm. This started life as a Simulink model, and what I've done is translate every block, the PV array, the power electronics, and the control loop, into plain MATLAB code, so you can see exactly what's happening under the hood instead of it being hidden inside blocks. By the end of this video, you'll understand the single-diode PV model, how the boost converter equations work, how P&O hunts for the maximum power point, and how the PI controller turns that into a real duty cycle. Let's get into it. So, here's the big picture. On the top row, we've got the actual power hardware. The PV array feeds into a capacitor C1 that feeds the boost stage, which is just an inductor, an IGBT switch, and a diode, and then C2 and the load resistor sit on the output. On the bottom row is the control loop, and this is the part that's actually smart. Once per switching period, the controller samples the PV voltage and current, runs the Perturb and Observe algorithm to decide on a new reference voltage, feeds the error into a PI controller, and that PI output gets compared against a triangle wave to generate the actual gate signal for the IGBT. So really there are two different clocks running in this simulation, a very fast one for the circuit itself, and a slower one for the control decisions. Keep that in mind, because it shows up directly in the code. Let's start with the PV array itself. This uses the standard single-diode model. If you've worked with solar cells before, you've seen this equation. Current equals the light-generated current, minus the diode current, minus the current lost through the shunt resistance. The tricky part is that current appears on both sides of the equation. It's implicit, so the script solves for it using Newton-Raphson iteration, 60 iterations max, until it converges to within a tiny tolerance. That gives us the current for a single module. Then we scale up. Divide the array voltage by the number of series modules to get the per module voltage, solve for current, and multiply by the number of parallel strings to get the full array current. On the right, you can see the actual parameters I used: 47 parallel strings, 10 series modules, 60 cells per module, and these are all modeled at standard test conditions, 1000 watts per square meter and 25 degrees Celsius. Now for the actual power stage. Instead of using Simulink solver, I wrote out the circuit differential equations directly and stepped them forward with explicit Euler integration, using a 1 microsecond time step. The voltage across C1, which is the PV terminal voltage, always follows the same equation. The PV current coming in minus the inductor current going out, divided by the capacitance. But the inductor current and output voltage equations change depending on whether the IGBT is on or off. When it's on, the inductor is basically shorted to ground through its small on resistance, and the output capacitor just discharges into the load. When it's off, the diode turns on, and the inductor current flows into the output, charging C2 and feeding the load. There's also a discontinuous conduction check. If the inductor current would go negative, we clamp it to 0, since current obviously can't reverse through that diode. So how do we decide when the IGBT is on or off? This is the simplest part of the whole script, honestly. We generate a triangle wave that ramps up and down between 0 and 1 at the switching frequency. I assumed 5 kHz here, but you change that to match your actual hardware or Simulink model. Then it's just one line. The gate turns on whenever our duty cycle command is greater than or equal to the current value of that triangle wave. That's a classic PWM comparator, and it's exactly what that greater than or equal block in the original Simulink diagram is doing. Let's take a look at the slide showing Perturb and Observe image, which illustrates the power versus voltage curve, or PV curve, for a solar panel utilizing the Perturb and Observe MPPT algorithm. The vertical axis represents the PV power in watts, while the horizontal axis tracks the PV voltage in volts. Our main goal in maximum power point tracking is to find and stay at the very peak of this curve, labeled here as the MPP. At this exact point, the system achieves maximum power and maximum voltage, and mathematically, the slope of the curve, delta P over delta V, equals 0. Notice that the curve is divided into two distinct operating regions. If we look to the left of the MPP, At point A, the operating voltage is too low, and the power is below its maximum potential. In this region, the slope is positive, meaning delta P over delta V is greater than 0. When the algorithm detects this positive slope, it knows that increasing the voltage will increase the power, so it takes action to increase VPV, moving us up the curve. Conversely, if we look to the right of the MPP, at point B, the system has overshot the ideal voltage. Here, the slope is negative, meaning delta P over delta V is less than 0. When the algorithm reads a negative slope, it realizes that further voltage increases will only drop the power, so it takes action to decrease VPV, pulling us back toward the peak. Finally, notice the curved arrows at the top. Because environmental conditions like sunlight and temperature change constantly, the Perturb and Observe algorithm never completely stops. Once it reaches the peak, it will continually introduce small voltage adjustments, causing the system to gently oscillate back and forth around the maximum power point to ensure we are always tracking the highest possible efficiency. Now, the actual MPPT brain. Perturb and Observe is beautifully simple. Every control update, we measure power, compare it to the last reading, and nudge the voltage reference a small step in one direction or the other. There are really only 4 cases, and I've laid them out here. If power dropped and we just moved the voltage down, that was the wrong direction, so we reverse and step up. If power dropped after moving up, we also reverse, stepping down. But if power went up no matter which way we moved, we just keep going that same direction because we're climbing toward the peak. There's also a safety check. If a step would push the reference voltage outside the allowed range, we just throw that step away and hold the old reference instead. This is the algorithm that, over time, walks the operating point up the power curve until it's hovering right around the true maximum power point, and then it just oscillates slightly around it forever, which is the one well-known limitation of basic Perturb and Observe. Once Perturb and Observe has decided what voltage we want, we need an actual controller to make the real voltage track it, and that's the job of this discrete PI controller. It's the classic structure. Take the error between measured voltage and the reference, multiply by Kp, add the integral of the error multiplied by key, and that becomes our duty cycle command, clamped between 0 and 1. The one detail worth calling out is the anti-windup logic. We only let the integrator accumulate error when the unsaturated output isn't already slamming against that 0 to 1 limit in the same direction. Without that check, the integrator can build up a huge value while the output's stuck at the clamp, and then it overshoots badly once it's free again. And just like the MPPT block, this entire PI update only runs once per switching period, not every single simulation time step, which mirrors that 1/z delay block feeding into the controller in the original Simulink diagram. Quick rundown of the numbers driving the simulation. The power stage steps forward every 1 microsecond. That matches the solver step in the original power GUI block. The switching frequency is assumed at 5 kHz, and we simulate a total of 50 milliseconds, which is enough time to see the MPPT settle. For the MPPT reference itself, we start at 300 volts, and it's allowed to roam anywhere from 0 up to 363 volts, taking 1 volt steps each time it perturbs. And every single time step, we're logging PV voltage, current and power, the reference voltage, the output voltage, the inductor current, and the duty cycle, so we've got everything we need to actually evaluate how well this thing performs. So once the simulation runs, here's what to look for in the plots. First, PV voltage against the reference voltage. You want to see the actual voltage converge onto the reference, and then just dither slightly around it, which tells you the MPPT loop is doing its job. Then PV power over time. This should climb up and settle near the theoretical maximum power point. The output voltage plot shows you the boosted voltage actually being delivered to the load. And the inductor current plot will show you the switching ripple from the PWM, riding on top of the average current. There's also a second figure that sweeps the array voltage and plots the theoretical IV and PV curves, with the true maximum power point marked, so you can directly compare where the algorithm settled against where it should have settled. Let's open the file I just shared. This MATLAB script is a standalone, numerical transcription of the Simulink model we studied in the previous video. In Simulink, we use pre-built Simscape blocks to model the physical components, but they can sometimes feel like a black box. By translating it into a MATLAB script, we are essentially writing the physics from scratch, exposing the differential equations and control logic exactly as the computer solves them. This will give you a much deeper, hands-on understanding of how the power electronics and the MPPT control algorithm interact in the discrete time domain. We are using explicit Euler integration with a fixed time step of 1 microsecond. Moving to the very first section, Section 1. Here, we define the physical characteristics of our solar PV array. We start with the topology of the array. It is made up of parallel strings, NP equals 47, and each string has ns_mod equals 10 modules in series. Each module has in cell equals 60 cells. Then, we define the intrinsic electrical parameters of a single PV module, which come directly from the manufacturer's datasheet or the Simulink block parameters. The light-generated current IL_N, the diode saturation current I0_N, the diode ideality factor N_diode, the shunt resistance RSH, and the series resistance RS_PV. We also pass in our standard test conditions. Temperature is 25 degrees Celsius, but we have to convert that to Kelvin, which is T_STC, and the irradiance is 1000 watts per square meter. Finally, we define our physical constants, the electron charge Q and Boltzmann's constant K. Using these, we compute the thermal voltage Vt per cell, which is physically around 25.7 millivolts. Now we look at Section 2, where we define the actual values of the power stage components. These values match the resistors, inductors, and capacitors we placed in our Simulink schematic. We have a boost inductor L of 1.45 millihenries, an input PV side capacitor C1 of 1000 microfarads, an output filter capacitor C2 of 3227 microfarads, and a 2-ohm load resistor R. Additionally, to make our simulation realistic, we model the non-idealities of the semiconductor switches. We add a small on-state resistance Ron_ict for the IGBT, as well as an on-state resistance Ron_d and a forward voltage drop VF_d for the diode. Note that we omit the snubber networks here, as they only affect high-frequency numerical ringing in Simulink, not the average steady-state behavior. In Section 3, we set the simulation time and timing parameters. The power stage integration step TS is set to 1 microsecond, which matches the Simulink power GUI setting. The switching frequency FSW is assumed to be 5 kHz, yielding a switching period TSW of 200 microseconds. We set a total simulation time of 50 milliseconds, which is enough to capture the startup transient. Because the PWM switch changes every 200 microseconds, but our power stage integration happens every microsecond, we calculate steps_per_control to be 200, meaning our control algorithm updates only once every 200 time steps. Following this, we set the MPPT Perturb and Observe (PNO) parameters, such as the maximum and minimum reference voltage limits, ref max, ref min, the initial reference voltage ref init, and the step size delta ref. We also define the discrete PI, controller gains KP, and key which we are assuming for this model. In Section 4, we initialize our dynamic state variables before the simulation loop begins. The state variables we are tracking are the PV terminal voltage V1, the inductor current IL, and the output voltage V2. All of these start at 0 to simulate a cold start condition. We initialize the PI controller's integrator memory, in_air, and the duty cycle output, control, to 0. We set up a digital triangular carrier wave variable, carrier and carrier_DHR, which will generate our PWM signal, and we initialize our reference voltage ref to the starting point. Finally, we pre-allocate arrays for logging VPV, IPV, and the inductor current over the simulation time. Pre-allocating arrays in MATLAB is a best practice. It makes the code run much faster by avoiding dynamically resizing arrays inside the loop. Section 5 is the heart of this entire script. Let's break down this for loop which runs from 1 microsecond up to the full simulation time. At the very beginning of each time step, We compute the actual PV output current using the built-in helper function PV_array_current. This current output depends on the present PV terminal voltage V1. Next, we generate the triangular PWM carrier wave. We increment the carrier up and down between 0 and 1 at twice the switching frequency, using the variable carrier_DSR to flip direction when it hits the limits. Now, pay close attention to this if statement. If mod kk1 steps_per_control equals 0. This line is extremely important. It ensures that the control loop, MPPT and PI regulation, only updates exactly at the beginning of each switching cycle, just like the sample and hold block in your Simulink model. Inside this block, we perform 3 actions. We run the pando_MPPT function to compare the present voltage and current with the previous values, and we perturb the reference voltage ref accordingly to push the panel toward its maximum power. We compute the error between the measured voltage Ms and the calculated reference ref. We run the discrete PI controller. Crucially, I have implemented integrator anti-windup here. If the duty cycle is saturated at 1 or 0, we only allow the integrator to update if the error would move the duty cycle away from saturation. This prevents the dreaded integrator windup, where the controller stalls during severe transients. The final duty cycle control is then clamped between 0 and 1. After the control update block, we implement the PWM comparator. We check if control is greater than or equal to the carrier wave. That determines whether the IGBT gate is on or OFF. Now, we solve the differential equations of the boost converter. This is done using the explicit Euler method. We have 2 conditions. If the gate is on, the inductor is shorted to the ground through the IGBT's on resistance. The diode is reverse biased, so the load is powered entirely by capacitor C2. If the gate is off, the inductor current flows through the diode to charge the output capacitor and feed the load. We also handle a special case here, discontinuous conduction mode, or DCM. If the inductor current reaches 0 while the switch is off, we forcibly keep it at 0, preventing it from going negative. Once we calculate the derivatives dV1, dIL, and dV2, we update the voltage and current states and then log them into our pre-allocated arrays. At the very bottom of the script, we have 2 essential local functions. The first is the PV_array_current function. Because the single-diode model equation is transcendental, you cannot analytically isolate I on one side of the equal sign due to the exponential term. We solve it using a Newton-Raphson iterative loop. We try up to 60 iterations until the change in current is less than 1 nanoamp. We then scale this module current to the full array current based on our series and parallel configurations. The second function is the pando_MPPT function. Notice that it uses MATLAB's persistent variables to remember the voltage, power, and reference voltage from the previous MPPT update cycle. By comparing the change in power, dP, and the change in voltage, dV, it decides whether to increase or decrease the reference voltage. This block exactly replicates the logic inside your Simulink MATLAB function block. Here's what's happening in both figures, based on our actual run. Figure 1, PV plus boost plus perturb and observe MPPT, time domain behavior. PV voltage tracking, top plot VPV starts at 0, shoots up past 300 volts in an overshoot during the first approximately 5 milliseconds. The boost converter and PI controller still settling from cold start, dips back down, then converges and tracks Vref tightly from about t equals 0.015 seconds onward. The ripple you see in the blue trace, once it settles, is the expected perturb and observe dithering. The algorithm is constantly stepping plus or minus 1 volt around the true MPP, so VPV never sits perfectly still. It oscillates in a tight band around Vref. PV array power. This mirrors the voltage plot's transient. Power spikes early, during the overshoot, since P equals V multiplied by I and both V and the operating point are swinging wildly. Dips, and then settles into a steady oscillation around roughly 1 times 10 to the power of 5 W, consistent with the approximately 100,084 watt theoretical MPP found in Figure 2. Boost converter output voltage. Vout climbs from 0 up to roughly 350 to 400 volts and settles there with visible ripple. This is boosted DC bus voltage. Note it's higher than VPV, which is exactly what a boost converter is supposed to do. Inductor current. Same story. A large initial transient spike, over 300 amperes, as the converter charges up, settling into a steady oscillating waveform afterward. The high-frequency ripple riding on top is the PWM switching ripple at our assumed 5 kHz. The slower oscillation underneath is the perturb and observe perturbation cycle. Figure 2, theoretical IV/PV curves, steady-state array characteristic. This is a static sweep, not a time domain result. It answers, what could this array do at 1000 watts/meters superscript 2, 25 degrees Celsius, independent of the converter? The IV curve shows the classic shape. Current stays nearly flat, approximately 375 amperes, for low to mid voltages, then knees over and drops sharply near open circuit voltage, approximately 360 volts. The PV curve is the real benchmark. It rises almost linearly with voltage, peaks, then falls off. My script found and marked the maximum point automatically, MPP, 290.2 volts, 100,084 watts. Putting the two together, my perturb and observe loop is doing its job. Vref in Figure 1 settles right around 290 volts, matching the theoretical MPP location in Figure 2, and the steady-state power in Figure 1 settles right around that 100,084 watt ceiling. The visible ripple in VPV and PPV isn't an error. It's the inherent steady-state oscillation of basic perturb and observe, since the algorithm has no way to rest once it finds the peak. It just keeps perturbing and rechecking forever. So to wrap up, what we built here is a faithful line-by-line translation of a Simulink power electronics model into plain MATLAB. The power stage runs on explicit circuit equations that switch behavior depending on the IGBT state, and the control loop runs PNO and PI, once per switching period, just like the sample and hold blocks in the original diagram. If you're adapting this for your own project, the two numbers you really want to double-check are the switching frequency and the PI gains. I made reasonable assumptions for both, but yours should match whatever your real converter or Simulink model is using. That's the full breakdown. If this helped, drop a like, subscribe for more MATLAB and power electronics content, and let me know in the comments if you want me to cover a different MPPT algorithm, incremental conductance, maybe in a follow-up video. Thanks for watching. See you in the next one.